Well, hello and welcome to the second episode of Arabial. I sincerely hope that this time you can actually hear me all right because this is my second time on Twitch, so I have no room for mistake anymore. Okay, so what are we doing here? We are basically looking at what's Tagbidal, how it works inside, how to use it to implement a distributed database, and just, well, learning about a fun piece of software. Uh, where we started in the first episode was looking at super high level philosophical kind of like considerations around why Tagebidal is written in such an unusual style, and also looked at one very specific instance of practical applications of all that philosophy, specifically the way we do networking. In the current episode, we basically continue with the same thing. There's going to be some hand-wavy philosophy, but also some very specific diggings into the code. So let's get started. Well, no one complains in the chat that I'm inaudible, so hopefully you can hear me. Okay, but first of all, I would like to thank this person for asking a question beneath the YouTube video. And the question was, why are we using reference counted messages? Like, can we just use owned messages and say what reference counted? And that is the excellent question, because I think it will take me two episodes to actually answer that. And this episode, the thing I was planning to talk about today, is actually a perfect half of an answer to this question about reference counting. But let's start with the recap. So what's Tagbidal? The purpose of Tagbidal is to track financial transactions. It's a database for tracking financial transactions. Finance are serious business. So the primary requirement for us is to be a reliable system. And a reliable system means that the system is safe, that if it operates correctly, it strictly follows the business rules specified, it won't lose your data, it won't create values out of thin air in general, kind of like, yeah, it's a reasonable system. The second aspect of reliability is availability, that not only the system works correctly, it also always works. There is like very little or no instances where the system says to you, hey, I cannot process your transaction. Like, if I process it, I will process it correctly, but sorry, come back later. No, we need to be online all the time. And to kind of like get to this availability, we need well, yeah, like kind of many a lot of things. One thing is like the generalized performance, because like although you like usually think about performance in terms of like just speed, like running fast, it also helps availability, because if you could run fast, but actually have to run relatively slow for the core workload, that means that you have a lot of headroom for unexpected changes in the workflow. And in general, you kind of like operate in the middle of the state space of a system, so you are more reliable. Uh, and kind of like basically, yeah, basically kind of like performance can be decomposed at like peak performance. How many transactions can you process on like the best hardware, and also or decomposed into efficiency. Like given the certain like load, what is the smallest amount of hardware you will need to process it? And kind of like both the peak performance and efficiency helps with availability in different aspects. So kind of like that's kind of like the ground level of availability. The thing which is kind of like really big deal, which really significantly impacts the architecture of the system, is the fact that the system needs to be distributed. If you want your system to be available, you cannot store everything on a single machine. You need to distribute it across different machines, either across different geographical regions, because otherwise one unfortunate asteroid can completely kill your system. Well, maybe an asteroid is kind of like unlikely, but like say a fire in the data center is a very real event, and it would be pretty sad to like lose all your data or all your system there. Okay, distributed systems are hard, and that's why one of the overarching architectural guidelines for us is that we try to build a simple system. Like, okay, it is distributed. That means it is not going to be like super simple. It means that we have a significant amount of fundamental complexity built in. But because we have this fundamental complexity, we try, like, well, we not try, we have to try, otherwise we would be able to build it, to reduce complexity elsewhere. And another kind of like super and wavy philosophical consideration that comes in is the consideration that we are really thinking long term here. Like we don't want to like release some database tomorrow which is built by like gluing pieces of existing systems, because we want to push this reliability envelope. We want to build a system which is more reliable than anything else, because we want our system to be usable in the context where you want to use the best reliability there is. That's basically what we want to be. We want to be like the most reliable system you could buy. And from this perspective, we don't want to rely on someone else's reliability, because if we use some other system underneath, that means that we cannot generally be more reliable than that system. And then the question arises, well, why do you need target at all? Why you can't just like use that underlying system? So kind of like we want to like build everything from scratch, which will take us longer in the short term, but in the long term, it would allow us, hopefully, well, it kind of like already is allowing us to not only push this like reliability, safety, availability boundaries, but also actually to move fast, because once you control your whole stack, you actually have superpowers, because, well, now if you need to do some kind of refactor across the whole stack, you don't need to coordinate with upstream, because you are upstream and you can just do this yourself. And kind of like frankly speaking, this all sounds horrifying. This goes against the usual wisdom in the software engineering, that software engineering is all about components. It's all about like composing components and like building on work of hours. And well, it's not like that. That's not true. That's like building larger software out of smaller components is the best way to build like, well, most kinds of software. But for kind of like technical, if you kind of like really want to nail down all these project properties, you generally don't want to use that. And kind of like as a sanity check, let's look again at that network parsing code to just compare it like as a napkin calculation of the number of source code lines with something more traditional. So again, where is our networking? We have like the definition of we haven't. Hey, where it is? Oh, there we go. Sorry, something was wrong. This is the last, but it seems okay now. Okay, so anyway, we have like this definition of what's our network message. As extract, it's an external struct, which means that layout of fields in the source code is actually significant and corresponds exactly to the layout of fields in memory. So this struct here specifies not only the logical contents of the header, but actually it's like physical layout on disk or on the wire or in memory. And then we have this what was called parse message, yeah. And then we have this message parse code, which isn't really a code at all. There's like really just like 2 lines. First, we just like cast the raw bytes to our header, and then we validate our cryptographically secure checksum, and that's the extent of our networking code. That is what we use instead of HTTP and gRPC. And those technologies are great. Those technologies allow different systems built by different teams to communicate with each other, to kind of like move fast without needlessly trying to solve global coordination problems. For our system at Targetable, because we control everything, we actually don't need that. And we can implement this really simplistic, but kind of like efficient and reliable communication protocol, which just casts messages. And again, just imagine the amount of code which would be required to like do this through gRPC. And think of not only about like the code like in your actual user space application, but also about like all the generated protobuffs, which like it's just giant what of that. I guess I don't think I've ever worked with systems which use gRPC, so kind of like that's something I've heard. This is not something I've experienced, but something I've experienced myself is like JSON, because Rust Analyzer, the repository for Rust, uses JSON to communicate with the editor, and really like 20% of the actual binary of Rust Analyzer is just the code for parsing JSON messages. Because it's kind of a cool, flexible format. It's not super performant, but performance is not relevant in the domain to that extent. And it's convenient. But again, to use that existing piece of technology, you need to push a lot of things into your actual software, which is okay in almost any case, except when you want to really, really, really push the understandability, the simplicity, the reliability of your system to the kind of unreasonable degree. Okay, so that was a quick 10-minute recap of the last episode. Let's now move to the next stuff. And what I want to discuss today is kind of like the actual logical model of data inside Targetable. So kind of like basically Targetable is a database. It means it stores data, and there are some kind of like queries or operations to change this data. And the question is, well, what is the data and what are the operations? So that's what we are looking at today. And the answer is like super simple. There's no SQL. There's no SQL. It's not document store. It is just double entry account. Now, I'm like not the right person to explain the benefits of double entry accounting because, well, I'm not an accountant, sadly. Well, or maybe luckily. So I'm not going to do that. I'm just going to describe the system and kind of like say, okay, this is good. And if you would want to know more about why this specific system for tracking financial transactions, well, you'd better learn that somewhere else and then go and tell me, because I would actually personally really love to learn more about this. Okay, so where is our domain? Yeah, I guess another question, another way to say this. Oh my dear, that was embarrassing, because I'm showing the code and I actually haven't switched my Twitch to the view with the code again. So this time I'm genuinely sorry. This is the second time I'm on Twitch, so I should not be making these mistakes. But we are making this. So yeah, mea culpa. On the positive side, this all is out there on the GitHub, on the IRL branch. So you could just go and read that. So yeah, the question in chat, is there a place where I can check the architecture of Tigerville? Well, there is like source code. There are a lot of, let me actually show this. There's documentation on the website, and there is like design internals. There's internals section, which actually documents a lot of things I will be talking about. But this is kind of like still pretty fragmented right now. So I don't think there is like super good single source for kind of like the overall architecture, which is like partially why I'm kind of like doing this Twitch show. Basically, yeah, I love architecture of Tigerville. I think it's like a beautiful thing. I want to explain it. If I had more time, I would actually go and write a giant blog post about this, or like maybe a book or whatever. But well, I don't have time. That's why I just like playing a document head here. Okay, where we are. Yeah, double entry accounting. So let's look at how it looks in the code. And this is all happens in the file tigerbeetle.zig. So tigerbeetle.zig is a file which defines our domain model. And it like really has like just two entities, two things. It has accounts and it has transfers, which is what you would expect from a software which tracks financial transactions. What is something a little bit unusual is that it's like double entry accounting. So let me explain this. So let's say we want to model a bank, like Alice, Bob, and Charlie, and they have a certain amount of money, like 100, 200, and maybe, I don't know, 100 again. And that's kind of like, yeah, like how you would naively model financial transactions. So kind of like just accounts from a certain amount. And like if you do some transaction, like send 50 from Bob to Alice, you would just go and let me compress this and change this to like this representation. So here we add 50, here we subtract 50, hey, that's transaction. That's kind of single entry accounting. The problem with single entry accounting is that it doesn't really give you strong invariance about the role consistency of all accounts. So for example, yeah, so here's like two states of the database. Here's like the third state of the database, where I say like Charlie has 600 money. And what you can say is that these two states are actually potentially from the same history, because the total sum on all accounts is the same. And this one is kind of like from a different history, because, well, the total sum is different. However, what you can't say here is if you consider these two states, you cannot say which one is correct and which one has a bug. So basically, in a single entry system, if someone manages to create money out of thin air, it's not immediately obvious from a current state of the system that this happened. And that is not property, because obviously when you track financial transactions, you really want to ensure that money are not created and don't disappear. So for fixing this, we can use double entry accounting, which says that each account has credits and also debits, which I, as not an accountant, confuse with each other. So sorry about that. And the invariant is sum of all credits equals sum of all debits, which kind of like doesn't make sense, because we cannot put 0 here, because, well, then this invariant doesn't hold. So in double entry systems, you usually have some kind of like treasury account, which kind of like creates the money. And this now works. So we have 400 on the credit side and 400 on the debit side. And like, in this system, you cannot just go and add like 50 or 500 to a single account, because that then this breaks invariant. So you also need to increase something in the debits column of, well, some other account. Otherwise, the difference between credits and debits for a current account doesn't change, which means that, hey, the amount of money doesn't change, and that's kind of like not what we want if you want to break the system. And that kind of like gives you like this credits equals debits invariant. It gives you some natural production that the overall state of the system is consistent. So anyway, sorry for this like super messed up introduction into double entry accounting. The main idea here is that is the best system humanity knows for tracking financial transactions, and that is what, like, in the broad strokes, trackable implements. So I guess I don't want to do super in depth into every little detail and every little feature which you support, and actually kind of like, given the amount of state we have here, we support surprising amount of things. But I want to describe kind of the general level. So first of all, things have IDs. Accounts have IDs, but transfers actually also have IDs. And IDs are actually pretty important in this system, because with transactions, one of the property you really want to enforce is idempotency, which probably we need to add in here. And while we rotate, let's actually come back and like, well, I've said, hey, double entry accounting, but why double entry accounting? Well, double entry accounting because it is a way to track financial transactions, very top level goal. But also, like, why not single entry accounting? Because double entry accounting has better invariance, it has better safety. The same thing goes for idempotency. Why do we want transfers to be idempotent? Well, first of all, because it is required for safety. If you can like replay the transfer and it applies again, that means that it is like, well, easy to double spend something or whatever. So that's like a bad property. Like if we want every transaction to either be recorded or not be recorded, we don't want it to be recorded twice. But also idempotency actually helps with availability, because if something is idempotent, that means that in the case of a failure, Or in the case where you don't know if it is a success or failure, you can just go and retry the transaction. So kind of like importantly, and that's why kind of like transfers and accounts have IDs. IDs. This follows from idempotency. Okay. So IDs. Then pending posted. Again, it's kind of like another bit of accounting terminology, but sometimes basically you want to do many phase transfers. You could say, hey, I'm going to transfer like 100 money if some event in the future happens. And then you kind of like credibly commit that you can send this amount of money, which means that like this amount of money is locked on your account, but it actually is spent only when the transfer is posted. Then we have user data. That's another kind of like interesting design decision. So as you've noticed, as you might have noticed, our domain model is fixed. Which means that if you kind of like want something different than this account, well, then you cannot actually use targetable unless you go check out the source and actually patch this new logic. This is really, really hard-coded in the source code of a database itself. The benefit here is that, well, this allows us to achieve better reliability, better efficiency, better safety, basically kind of, well, actually, I can refer this back to just like simplicity. Because the fixed domain model allows us to really focus on executing this domain model as efficient as possible. And it also actually, the only domain model we need to solve our purpose of tracking financial transactions. So kind of like, well, if you don't need custom domain model, then why would you use it? But this creates a problem. Like obviously, like financial transactions do not happen in the vacuum. There is some kind of like user account in a bank or whatever, which has some like other like useful information. Like for example, at the end of the day, you want to attach accounts to real people, and we kind of like, who is the real person? What identifies a real person is a hugely complicated question. And we like don't want to like, I don't know, hard-code first name, last name in our schema and then realize that, hey, there are like countries and cultures where like you have more or fewer names or like your names are not strings or whatever. So we don't do this. I would say that like our account ID is just integer, but we also allow plugging into arbitrary user data into this account, which is data which is not interpreted by the target at all. So this is like user data is something which the user sets when creating an account, and we like preserve it, but we don't look at it. And the purpose of this data isn't really like encoding things like first name or last name, because well, there is only like 28 bytes here, and that might not be enough. The purpose here is to encode primary key relationships with something else. So the idea here is that you have like Trivial, which tracks finances, and then you have like your normal Postgres or SQLite or maybe, I don't know, Mongo database, which tracks everything else. And then you have links between these two different data stores. Okay, that's like user data for you. Then some reserved fields for something we might need later. There's like the ledger, because we kind of like, we don't want to store just like one currency. We want to say, hey, kind of like, this is like your account in dollars, and this is your account in pounds. And for that, we need to maintain two separate ledgers, and that's basically what this ledger does. Code also, I actually don't know what would be like the practical use cases for the code, because I'm not an accountant, but again, it's kind of like reasonable that you might want to classify accounts. Then there are like accounts flags, And this one is actually pretty interesting. So debits must not exceed credits, credits must not exceed debits. This is exactly how you could do treasury accounts. So by default, like debits must not exceed credits, but well, if you have treasury, you actually want the opposite. And we have this link. No, we don't have this link. No, yes, we have this linked field. Linked field is actually how we do multi-entity transactions, basically transactions which span more than a single account or a single transfer. Which, yeah, let's keep it for now. Probably at some point we'll like dive deeper into the domain model. And yeah, kind of like that was the account. Now transfer again. The idea of the transfer itself, then IDs of the accounts which should transfer, then the amount, the same user data. This pendant is again for handling this like posted pendant stuff I was looking for, which again I don't want to dive into deeper. The same ledger, the same timeout for again pendant posted flags and timestamp. And yeah, that's the entirety of our domain model. Again, if you kind of do everything by hand, do everything from first principles, the actual amount of logic might be surprisingly compressed. It might be hard to arrive at it, like it took humanity millennia to arrive at table entry accounting. But now, once we like distilled that, hey, this is the domain model we need for financial transactions, coding it up is not that hard. And yeah, a whole bunch of errors for things which could go wrong, because well, many things can go wrong. Okay, so this probably wasn't super interesting because well, we are here for a database, we are not here for accounting, or at least I'm here for a database, but well, I guess I'm at least a little bit interested in accounting. Anyway, let's look how we actually run this code. And this happens in the state machine file. So that's kind of like this state machine .zig, and the fn execute is like the heart of Tidybuilding. This is where like money actually gets transferred from one account to a different account. And this is actually curious. Like you would expect that this accepts like an account, well, or maybe like an array of transactions. But here we accept just like byte buffer and another byte buffer, so kind of like where's the main model, and this ties back into our networking protocol because remember message that on the network level we exchange messages, and messages are stupidly simple. They consist of like just a byte buffer where the first some amount of bytes are the header and the rest is the body. And the contract for the main model in Tidybuilding is that it just accepts a body of a message, and then it processes the body in however it wants. But the curious thing here is the actual body here, like this input, turns out to be an array of the main object. So this thing is going to be an array of accounts or an array of transfers. And why is it? Why is this like single transfer, not a single account? Well, the kind of like super high level philosophical motivation here is that this is mechanical sympathy. Well, okay, no. This one is actually not yet mechanical sympathy. This is something different. So what we are doing here is that we are batching events. We don't process a single account or a single transfer at a time. We always process a whole slice of them. And the reason for this is the combination of the fact that this is a distributed system, so it needs consensus. Let's try to shift indexes there. So we need consensus. I'm not going to get into consensus this time. But one thing I want to say is that consensus means that you have like a bunch of machines and they communicate with each other over the network to arrive at a decision. And communication over the network generally has like non-trivial latencies. Like latencies and throughput today actually might be much less than what you would expect to see. Like networks are really fast these days, but still it is kind of like way slower than going to like a register in the CPU. So kind of consensus has overhead, and the way you solve this overhead is with batching, because if you run consensus route for every transfer, well, that's slow. What you could do is you could instead run consensus for like 1,000 transfers. And that means that the overhead of consensus itself gets divided by 1,000. So again, we use batching because consensus is slow and we care about performance. And that's why we kind of like try to amortize the cost of consensus. So yeah, that's kind of like why would we expect to see a batch here? But what is surprising? If you kind of like just think naively, what you would like do probably is you say, okay, so actually kind of like a batch is an array of events where an event is actually an element, which is like to try to type Z contrast here, which is like a create account or like make a transfer. This is not what happens here. What we actually do in this state machine execute code is that our batches are always non-polymorphic. So this is actually a slice of accounts or a slice of transfers depending on this compile time iteration parameter. So again, we don't ever mix different events in a single batch. Batches are uniform. So that means that actually the way our batch ends up looking is this: slice of accounts or slice of transfers. And to kind of like, again, that's like this thing on the right is like very hand-wavy explanation. Let's actually physically look at how that is implemented in the code. So this execute is parameterized by iteration. Iteration is just an enum tag, which says what kind of batch is there. Is it like creating accounts, creating transfers, or looking up accounts, looking up transfers. Then, when we start executing the iteration, the first thing we do is we go and cast our input to the appropriate event. So if the event is create transfers, then this thing at compile time gets to be an array of transfers. If it is an account, then it gets to be an array of accounts, etc., etc. And then we just, go through this batch and execute events essentially one by one. So this chain stuff is what I was alluding to with the links field. So basically, you could say there is like 10 transfers, they're all linked, and either they all pass or they all fail. And this logic is actually shared for all events. So again, you can create accounts and say, hey, either create all these 10 accounts or create none of them. And it also works for transfers. And then we actually go and like process a single transfer where like a lot of logic to handle all the possible error conditions, including overflows, and then where it is, yeah, and then like this is kind of basically it. Just like add debits and credits over two appropriate accounts. Like everything else is like basically just error handling, which there is a lot of in financial transactions. Anyway, so again, that's kind of like the nutshell of how business logic gets executed in targetable. There is like this hard-coded double entry accounting. There is this execute method in the state machine, which takes a non-polymorphic batch of objects and, well, just goes and does the thing. And the question is, like, why non-polymorphic batch? Like, why just, again, like, we need a batch because we need consensus. But why do we need a non-polymorphic batch? And the reason for that is that mechanical sympathy, which I've added here, and then quickly edited that. So. And let's see if we need to adjust any indexes. Yeah, if this were in, I would actually be able to use some macro here, but well, that's not Vim, so here we have. Okay, so non-polymorphic batch comes from the need to do batching and from mechanical sympathy. But what the hell is mechanical sympathy? Well, mechanical sympathy is actually just another name for efficiency, really. It's basically the idea that when you write high-performance code, you want to write a code close to the underlying machine. You want there to be no impedance mismatch between what you write in your source code and what your CPU actually executes, which is another way to say, well, mechanical sympathy is basically do what CPU is best at doing. And one thing that CPU is good at is precision code and instructions and basically execute on tight loops. So if you execute the same code again and again and again, then CPU gets really good at predicting all the branches, really good at putting all that code into its instruction cache. So kind of like executing a tight loop over a huge amount of data is fast. What is slow is, well, executing many different operations on the same amount of data. Because, well, if the CPU first needs to create 100 accounts, but then it needs to create 100 transfers, when it switches from creating accounts to creating transfers, all the branches are different. So the branch predictor needs to learn again what are the branches. You need to load all this code into instruction cache, etc., etc. And well, kind of like if we run ahead of ourselves, like this also prevents vectorization. We don't do vectorization right now, but that's something we might consider doing in the future. So basically, the idea here is that if you make your branches, your batches, not non-polymorphic, you just push the branches at the top of your code. So coming back here, in non-polymorphic batch, we have this one single branch at the top level for a whole batch. And then inside this, we just go and always execute the single action. Again, this is fine. So it looks like there is a branch in here, but actually operation is comp time. So now I don't want to sync my settings. I want to go to definition. Operation actually is a comp time parameter. So there isn't branch here. There is just like straight line code to one of the two functions, which is in line, which is then folded into like this overall scaffold for handling events, which leads to kind of like fast CPU execution times. So kind of like this explains like why our domain model kind of like, well, why we execute domain model in batches, why we kind of like, we have individual transactions in our domain model, but in our like physical realization of the domain model, we always think about like many things, many transfers, many transactions. And this, as it promised, answers one of the questions here, like why we are using reference counted messages? Why we are not using old messages to save all of those ref count increments? And the answer here is that our message isn't really a message, a single thing. It always carries with it a batch of operations. So operations with a reference count of a single message actually operate on 8,000 of like actual atomic events in our system. And that means that the overhead whatsoever for reference counting of the messages is negligible. I mean, it is negligible even kind of like in absolute terms, because well, like yeah, this is running ahead, but we are also like doing. I see a cycle here that's not great. Non-polymorphic batch comes from mechanical sympathy. One thing I will go to at some point is that our code is actually single-threaded. So reference counting is non-atomic reference counting, and that is like super cheap. And it is amortized across the whole batch. But more importantly, consensus. Where is consensus? Consensus is amortized across the whole batch. So yeah, that's kind of like not really a performance question. Then what is left unanswered is, well, why we are using reference counting if not using reference counting is simpler. Like reference counting sounds like complicated, and well, when you write Rust code, usually when you do arc and mutex and whatever, like someone will go and ask you, hey, could you just like use ownership? That's going to be simpler, and that's like usually true. But for messages, we have like a very good reason to actually ref count them, and we'll get to that hopefully in a week. Actually, I haven't mentioned this before, but I promised that this is going to be a bi-weekly series. Well, I lied to you. This is going to be a weekly series because I'm having a blast just like talking through, and really, I don't know. I don't know how many bullet points we will need here, but probably quite a few. So I'm sorry. Sorry, it's not good. Again, as I said, if I had more time, I would actually like write a book here. I don't have time, so you will have to endure my blubbering. Okay, so reference counting is really not a performance problem, because we do batching, and batching amortizes over stuff. And reference counting is actually kind of like minor overhead, which we amortize around. The major overhead is consensus. Okay, so kind of like, yeah, recent batching. This kind of like has interesting implication because, well, okay, let's say I'm like in the show and I want to buy something. I want to buy a computer. The problem is like I want to buy a single computer. Like I don't want to buy 8,000 computers. So kind of like all the system like does batching, and batching is faster. Like I, as a consumer of a system, want to submit only a single transaction. And kind of like if I submit a batch of 8,000, like a batch whose size is 8,000, but only one transaction is used, of course, then batching is just pure overhead. Like, why would you do this? Sorry. And that's kind of like brings us to another like pretty big thing in the design of Targetable is that clients are API gateways. So when I go to the shop to buy a computer and make a payment, my phone or well, rather like whatever thing I'm using to make a payment doesn't talk to Targetable directly. Rather, it talks to an API gateway. So let's say, let's try to draw some ASCII diagram here. So we have a bunch of end users, and they all talk to API gateway. So kind of like a single computer, mobile phone. And the computer in a cloud, and the API gateway. Okay, so here we have like one transaction. And the API gateway assembles a batch, and then it sends it to Targetable, which is a cluster of 6. So yeah, that's why when I'm talking about client in Targetable, I don't actually mean like this end users. I mean this like API gateway. And like one reason why this is a good idea is well, because we use batching, so like you can just not expose this to the end user. But there is also kind of like another good reason is that this link here between users and API gateway is like public internet. And like public internet is like a horribly scary place. Like there's like all kinds of like malicious things there. Like there's like even all kinds of like non-malicious things there, like the gRPC and HTTP. So you kind of if you build like a really reliable system from first principles, like you don't want to talk to the public internet. Because again, coming back to our messages, like just, I mean, if you come with this to public internet, the public internet will say to you like, hey, I don't speak this. Like I like need HTTP. I have like very specific protocols which are supported by my routers. Like, well, whatever. Like this is kind of this is some garbage. So you want to handle this communication with a variety of protocols in the internet centralized in some other system, which might be less reliable, but that is okay because it is stateless. And then that system's kind of like out of this information, it cleans it up, it makes sure that no one is trying to attack you, no one is trying to do a denial of service kind of an attack. And after that, just like goes and sends the data to you. So let's complete this architecture diagram. So this is like public internet, this is like private intranet. It's like probably like cloud internet or whatever. Here we have like untrusted HTTP. And here we have trusted bytecasts. And this explains one cliffhanger I left from the last episode, that when we do checks and validation here, this protects us, well, kind of like this proves correctness of our casting here, assuming that the person we're communication with is not malicious. And you cannot assume that over public internet, but you can totally assume that when you communicate with an API gateway, because you control both the gateway and the trigger middle. So let's say it here, non-Byzantine. And the reason why we can assume non-Byzantine networking is that our clients are actually API gateways. So again, I don't think we have a cycle here, but you see that like this thing here like starts to be like more convoluted and like more hard. So probably at the end I would have to like write a script to like a topological sort here and like, detect strongly connected components of ideas or whatnot. But you see, like this is interesting. Like we have like this orthogonal ideas which start to interlock and which start to define the architecture of our system in big ways. So again, let's unwind this. We need a distributed system because we want to be available. For distributed system, we need consensus. Consensus is not as fast as some other things. So we want to amortize over the cost of consensus. That means that we need to add batching. But batching means that we need to have API gateways to aggregate requests from end users into a batch. But if we use API gateways anyway, that means we are not communicating with end users directly. That means we can actually assume that all our peers in the network are trusted, and we can function in a non-Byzantine environment. And that in turn means that we can massively simplify our network parsing code because we can just trust that the other side is behaving correctly. You don't need to trust that it's behaving correctly, but we can trust that it's not trying to like deliberately subvert us. And that leads to huge simplification in our networking parsing code. So kind of like, yeah, you see how everything starts coming together. Okay, let me think if I want to cover anything else, and also actually check if there are any questions in the Slack channel. Yeah, so what's Iron Beetle? Well, Iron Beetle is the name of the show, which is a terrible pun on me being a fan of Judas Priest and me working at the Trigger Beetle database. What keyboard do you have? Well, kind of like a keyboard. It doesn't really matter. Like it types. I'm a horrible typer. But isn't really kind of like my bottleneck or my strength. Okay, I guess that covers the question, and we probably can wind this down and look for what are we going to talk about next week. Yeah, I guess kind of like as a teaser, today we've answered like how this question, specifically that hey, because we do batching, we don't care about overhead of runtime overhead of reference counting. Next week, I guess we will take a single message and see how it flows through the entirety of our system, starting at the network layer, going through this execute function we've seen today, and ends up right on the hard drive, which would explain why we actually kind of fundamentally need reference counting and why we can't get rid of it even for purpose of simplicity. Okay, I guess that's it for today, folks. Then again, sorry for forgetting to actually share my screen for the first like 5 minutes or so of the video. Next time, please note this and write me in Slack that, hey, Matt, you're like being super stupid. But hopefully next time I will be twice as much experience at Twitch as I am today, and it's going to be even better. Thank you for listening, and see you in a week.